present video lecture, we'll discuss about interrupt hardware, enabling and disabling of an interrupts, handling multiple devices. So first we'll consider interrupt hardware. So the diagram shows an equivalent circuit for an open drain bus used to implement a common interrupt request line. Consider the case where all external devices request for a service over a common interrupt request line. All devices are connected to the interrupt request line via switches to the ground. If all signals INTR1 to INTRN are inactive, that means all the switches are open. All the switches are open. Switches are open. The voltage on the interrupt request line will be VDD. So whenever the switches are open, the voltage on the interrupt request line, that is nothing but VDD. And hence no interrupt signal is generated. In order to raise an interrupt request, the device closes its switch. The device closes its switch. So in order to raise an interrupt, the device closes the respective switch and the voltage across interrupt request line becomes 0. Since the switch is directly grounded, so the voltage becomes 0. Hence, the value of INTR is the logical OR of the request from the individual device, that is, so the overall interrupt request INTR, that is equal to INTR1 plus, that is logical OR operation 2 and so on, INTRN, so till n devices. In order to implement, we considered open collector, that means open drain gates, to drive the INTR line. The output of such gates is equivalent to a switch to the ground that is open when the gate's input is in the state 0 and closed when it is in the state 1. The voltage level at the output of the gate is determined by the data applied to all the gates connected to the bus. So we are also having one more register R, that is nothing but pull-up register. So register R is also called as pull-up register, which is used in order to pull the line voltage up to the high voltage state when the switches are open. When a request is received over a common interrupt request line, additional information is needed to identify the particular device that is activated the line. The information is available in the status register. The information will be available in the status register. Status register. So suppose if you are having n devices which are connected to the single interrupt request line, in order to raise an interrupt, the respective device need to close the switch. In order to raise an interrupt, the respective device switch will be closed so that the voltage across the single interrupt request line equal to 0. So I can say that across the processor we are having one NOT gate. So input to the NOT gate is 0 and output is 1. That is how the interrupt can be enabled with respect to the processor. That means the processor gets the information regarding the device interrupt which was placed on the single interrupt request line. So whenever the switch is open, the voltage across the single interrupt request line, so that is, I can say that it is somewhat high. This voltage will be high. Suppose if this voltage is not exactly equal to VDD or maximum voltage VDD. So we are having one more register, that is pull-up register, which will boost the voltage up to VDD. So since the voltage across single interrupt request line is high, so that means I can take it as logic 1. High means logic 1. So input given to the NOT gate, if it is 1, and output will be 0. So that means not even single device, not even single IO device are placed its request on the single interrupt request line. So we are also having one status register which holds the additional informations like some flag bits like FIN and FOUT followed by interrupt enable bits for keyboard as well as display. When a device raises an interrupt request, it sets one of the bits in its status register called as interrupt enable bit, that is IRQ bit. So we can consider for keyboard, in the status register we are having a single bit called as KIRQ, and for display we are having DIRQ. So these two bits are used in order to raise an interrupt with respect to the keyboard as well as the display. In any of these bits are 1, the particular device has requested the service. Also, if 2 or more devices have activated the line at the same time, then one of them will get the service first, followed by the other device waiting for the service. If both keyboard as well as display has raised its request, that is interrupt request, among two devices, one device will win the task and it will get the service, that is interrupt service, and other device need to wait for the service. The solution for handling multiple requests occurring simultaneously is known as arbitration. So if you are having more number of IO devices are requesting for an interrupt, so we have to consider arbitration process. So arbitration process identifies which respective device can win the task and which will get the service by the processor. So we are having 3 different methods by which arbitration process can be considered. So the first one is pooling. The first method is pooling. The second method is vectored interrupt. And the third one is priority assignment. To request an interrupt, a device closes its associated switch. Thus, if all interrupt request signals are inactive, the voltage on the interrupt request line will be equal to VDD. When a device requests an interrupt, the voltage on the line drops to 0. This causes the INTR received by the processor to go to 1. The value of INTR is a logical OR of all the requests from individual devices. Like INTR is equal to INTR1 plus INTR2 plus so on till INTR n. A special gates known as open collector or open drain are used to drive the INTR line. The output of the open collector control is equal to a switch to the ground that is open when gate's input is equal to 0 and closed when the gate input is equal to 1. Register R is called pull-up register, which is used in order to boost the voltage to VDD. Enabling and disabling interrupts. When an interrupt arrives, the processor suspends the execution of one program and begins the execution of another program which was requested by the external device. Since interrupt is an asynchronous event, it may alter the sequence of events already being performed by the processor. Hence, facility must be provided to enable as well as disable interrupts as desired. This can be performed by the processor itself or by the user under program control. Consider the case of a single interrupt request from one device. The device keeps the interrupt request signal activated until it is informed that the processor has accepted its request. This activated signal is not yet deactivated. That may lead to successive interruptions, causing the system may enter into an infinite loop. For example, if we are considering a single IO device and one processor. This is nothing but processor. So now IO device initially request for an interrupt. And the processor is ready to give the service and it will send an acknowledgement INTA signal. And the processor is provided the service which was requested by the IO device. But even after receiving the service or getting the service by the processor, this IO device holds the INTR request within itself. So now already processor is provided the service to the IO device, but even after IO device holds the request, that is interrupt request. Now the processor may think that once again IO device wants its service and it will provide the service. So once again it will provide the service. So if the enabled request, if it is not disabled at the IO side, so the processor will keep on providing the service. So that may lead into an infinite loop. That means, so the activated signal, if not deactivated, may lead to successive interruptions. So there may be a n number of interruptions causing the system to enter into an infinite loop. In order to overcome from this, so we are using three different techniques. So in the first technique, the processor should ignore the interrupts until the execution of first instruction of the ISR. The processor should automatically disable interrupts before starting the execution of ISR. The processor has a special INTR line for which the interrupt handling circuit may respond only to the leading edge. So in the case 1, so we know that we are having initially the processor will ignore the interrupt request line, that is INTR line, until the execution of first instruction of the ISR. So whenever the interrupt is called, the set of instructions which were executed are called as ISR. So in the case of technique 1, the processor ignores INTR line until the execution of first instruction in the ISR. So now what is that first instruction in the ISR? So that means the first instruction itself within ISR is interrupt disable. It will, that is nothing but initially itself we can disable the interrupt. So by using interrupt disable instruction at the beginning of ISR, the programmer can ensure that there is no further interrupt may occur with respect to that IO device. So now the actual execution of programs will take place within the ISR. Before returning from the ISR, that means at the end of the ISR, once again we can enable that, because that IO device that is interrupt enable, because the IO device may need interrupt enable signal in future. So that is how we can enable as well as disable in order to avoid an infinite loop with respect to the INTR signal. So in the case of technique 1, the processor will ignore the INTR line unless or until the execution of first instruction in the ISR. So the first instruction in the ISR is interrupt disable instruction, and after that it will execute some set of instructions whatever present under ISR. So finally the processor will enable, that is interrupt enable instruction will be placed before the return from the interrupt instruction, which is used in order to enable the interrupts again. So the second technique is using processor status register. The second possibility to have the processor automatically disable the interrupts before starting the execution of ISR. So in the second technique, the processor automatically disables the processor automatically disables the interrupt request, that is disables the interrupts before starting the execution of ISR. So in advance to this, the processor should save the contents of PC and the processor status register on the stack. So in the second technique, the processor will save the content of PC as well as processor status register, that is PS within the stack. The processor status register has one bit called as interrupt enable bit. The processor status register, that is PS register, has one bit, so that is interrupt enable bit. So this bit is used in order to enable or disable the respective interrupts. The processor status register interrupt enable bit will enable interrupts when IE bit is set to 1. After saving the contents of PS register on the stack, the processor clears the interrupt enable bit and its PS register, disabling further interrupts. So in the case of processor status register, it consisting of one interrupt enable bit. So initially the processor will copy the PC as well as PS value into the stack, and after copying the content of PS as well as PC into the stack, the processor status register IE bit will be disabled. So within the stack, the IE bit will be set to 0 in order to avoid the further interrupts. When a return from the interrupt instruction is executed, the content of PS registers are restored from the stack, and once again the contents can be retrieved from the stack, and the PS content within the PS IE bit will be set to 1 in order to enable an interrupt in future. So the last approach, that is third approach, in which the processor has a special interrupt request line for which the interrupt handling circuit responds only to the leading edge of the signal. Such an interrupt line is called as edge triggered. It's called as edge triggered. In this case, the processor responds only to the edge and not to the level of the interrupt request signal. Thus, there will not be multiple interruptions because of a single request, and hence no need to explicitly disable interrupt request from this line. Sequence of events involved in handling an interrupt request. The device raises an interrupt request. The processor interrupts the program currently being executed. Interrupts are disabled by changing the control bit in the processor status register, that is IE bit in the case of processor status register. The device is informed that its request has been recognized. In response, the device deactivates the interrupt request signal. The action requested by the interrupt is performed by the interrupt service routine, that means ISR. Interrupts are enabled and execution of interrupt program is resumed. Handling multiple devices. While handling more than one I/O devices, the issues concerned are: how can the processor recognize the device requesting an interrupt? How can the processor obtain the starting address of the appropriate ISR? Should a device be allowed to interrupt the processor while another interrupt is being serviced? How should two or more I/O devices request can be handled by the processor? Because different device may require different ISRs, how can the processor obtain the starting address of the appropriate routine? Different approaches are used to resolve these problems depending on the given applications. The solution to handling multiple interrupt requests occurring simultaneously is known as arbitration. So we are having three methods by which we can perform arbitration process. The first one is pooling, the second method is vectored interrupts, and the last one is priority assignment. The simplest way to identify the interrupting device is to have the interrupt service routine ISR pool all the I/O devices connected to the bus. So in the case of pooling, so the interrupting device is to have the ISR, that is interrupt service routine, which will pool all the I/O devices which are connected to the bus. The first device encountered with the IRQ bit, interrupt enable bit, is the device that should be serviced by the processor. After servicing that respective device, the next device may be serviced by the processor. So here in the case of pooling, we can consider a single status register with the following field, that is DIRQ, KIRQ, KEN, DEN and two status flags like SIN and SOUT. DIRQ, which is used in order to enable an interrupt request for the display. Similarly, KIRQ, that is interrupt request for keyboard, KEN, keyboard enable signal, DEN, display enable bit, and SIN and SOUT are two status flag registers. For an input device, SIN status flag is used. So whenever SIN is equal to 1, when a character is entered at the keyboard. When SIN is 0, when the character is read by the processor. So here we can observe that we are having data in, data out, two buffer registers followed by status register and control register. So the status register consisting of DIRQ, KIRQ, SOUT, SIN, and the control register consisting of DEN and KEN bits. So these are the 4 different registers can be considered with respect to keyboard as well as display interfaces. So next is vectored interrupts. A device requesting an interrupt identifies itself by sending a special code to the processor over bus. Then the processor starts executing the ISR. The special code indicates the starting address of ISR. The special code length ranges from 4 to 8 bits. 4 to 8 bits. The location pointed to by the interrupting device is used to store the starting address to the ISR. In the case of vectored interrupt, so we can reduce the time involved in the pooling process. So in the case 1, the processor takes longer time in order to identify which respective devices placed its request, that is pooling process. But the vectored interrupt reduces the time involved in the pooling process. The design may be such that the device may identify itself to the processor. So in the case of pooling mechanism, the processor will check the status of I/O. Here the I/O device itself gives its identity to the processor. So in the case of pooling process, the processor need to check the status of all the I/O devices. So it takes longer time because the processor simply need to check the status of all the I/O devices. Instead of that, we can consider in the reverse fashion. That means the I/O device itself can give its identity to the processor. The I/O device itself can give its identity to the processor. So how it can give the identity to the processor? That means by sending a special code. So it will place some special information or special code over the bus. So I/O device, it will place some special code over the bus. So now what is the size of this code? So the length of the code ranges from 4 to 8 bits. Usually the code is nothing but the starting address of ISR. The device which is willing to interrupt the processor, so it can directly gives its identity by sending a special code to the processor over the bus. The size of the code length ranges from 4 to 8 bits. Usually the I/O device, it will place the starting address as code on the bus. The location pointed to by the interrupting device is used to store the starting address to ISR. So the vectored interrupt reduces the time involved in the pooling process. So compared with the pooling process, vectored interrupt can be considered with more efficiently. The starting address to ISR is called as interrupt vector. The processor loads the interrupt vector into PC and executes appropriate ISR. Already the processor has the code value. Within the code, it consisting of the starting address of ISR, starting address of interrupt service routine. So now After that, the processor will load the code value into PC and execute the appropriate ISR. When processor is ready to receive interrupt vector code, it activates INTA line. So whenever the processor is ready means it will activate INTA line. Then IO device responds by sending its interrupt vector code and turning off the INTR signal. The interrupt vector also includes a new value of the processor status register. Controlling device request. So we can make use of some set of condition codes like KEN, DEN, KIRQ and DIRQ in order to enable or disable an interrupts. There are two independent methods are for controlling interrupt request are IE bit, that is interrupt enable bit, at the device end. IE bit in a control register determines whether the device is allowed to generate an interrupt request. At the processor end, the interrupt request is determined by IE bit in the processor status register, that is PS register, or else by using priority structure. Interrupt nesting. So we can have two possibilities. Either multiple requests coming over a single interrupt request line, or else multiple requests over multiple interrupt request line. So in the case of interrupt nesting, we can consider two factors. Either multiple requests are coming over a single interrupt request line, or else over a multiple interrupt request line. So here we can have more number of devices, like I can consider device 1, device 2 and device 3. So which is connected to a single arbitrator block. So that is called as priority arbiter. The devices are connected to the priority arbiter. So this will choose one INTR request and that request will be placed on the processor. Each INTR line is assigned a different priority levels. Priority levels will be assigned with respect to the devices D1, D2, D3. The priority level of the processor is the priority of a program that is currently being executed. The priority of the processor can be considered with respect to the program which is currently being executed by the processor. Processor accepts the interrupt only from the devices that have higher priority than its own. The processor can accept any request by the devices only if the priority of such devices are more than that of the processor priority. At the time of execution of ISR, for some devices, priority of processor is raised to that of the device. Thus, interrupts from the devices at the same level of priority or lower level can be disabled. So now we'll consider privilege instruction. The processor's priority is usually encoded in few bits of the processor status word. It can be changed by the program instruction called as privilege instructions, which write into the processor status word. These instructions can be executed only when the processor is running in a supervisor mode, that is, while executing the operating system routines. The processor switches to the user mode before beginning to execute application program. This will guarantee that a user program cannot change the priority of the processor. That means the user program cannot accidentally or intentionally change the priority of the processor as well as it can disrupt the system operation. So an attempt to execute a privileged instruction while in user mode leads to a privilege exception. So an attempt to execute a privileged instruction while in the user mode. So that is called as privileged exception. So the privileged instructions are executed in user mode. So that is called as privilege exception. The second scheme, which is nothing but implementation of interrupt priority using individual interrupt request and acknowledged lines. Devices are organized into groups and each group is connected at a different priority levels. So for individual device, so that is it has its own priority. So the priority arbitration circuit, it checks the priority which was assigned by the processor. So depending upon that, the respective device will get the service by the processor. So here the daisy chain arrangement of devices is considered in the diagram. Suppose the device 1 places its request on the single interrupt request line INTR, I can take it as 1. So now with respect to this request, with respect to INTR1, the processor will issue an acknowledgement signal, that is INTA1 signal. So INTA1 signal. So now the device will receive the acknowledgement by the processor and it will get the service by the processor. For example, device 2 is placed its request on the single interrupt request line. So that is, I can consider it as INTA2, I'll consider dash. So now the processor checks the single interrupt request line and it observes that there is one request, that is INTR request, which was placed by device 2. So now what exactly the processor does is, with respect to that request, it will send an acknowledgement, that is INTA2 dash. So now, this INTA signal will be propagated through device 1. So device 1 will receive that acknowledgement signal, but the device 1 is not raised any request, or which is not placed any request on the single interrupt request line. So at that instant, an acknowledgement signal will be propagated to the next device. So that means if the device is not encountered any request, such acknowledgement signal can be propagated in a daisy chain fashion to the next device. So the INTA signal propagates serially through the devices and the respective device will get an acknowledgement by the processor and it will get the service by the processor. So this is how the simultaneous request can be handled by considering daisy chain fashion. The second one is arrangement of priority groups. So in the diagram we can observe that we are having within the processor, it consisting of priority arbitration circuit. When several devices raise an interrupt request and INTR line is activated, the processor responds by setting INTA line to 1. This signal is received by the device 1. If device 1 has requested the interrupt, it blocks INTA signal and sends its identifying interrupt vector on the data bus. If device 1 has not requested for the service, it passes INTA signal to the next device. Hence, in daisy chain arrangement, the device an interrupt is an event that causes execution of one program to be suspended and execution of another program to begin. Exception refers to any event that causes an interruption. For example, I/O interrupts. Kinds of exceptions are recovery from errors. These are techniques to ensure that all hardware components are operating properly or not. For example, many computer includes an error checking course or ECC in memory which allows detection of errors in the stored data. So we can also use ESR, that is exception service routine. If an error occurs, control hardware detects the errors as well as informs the processor by raising an interrupt. When exception processing is initiated as a result of errors by the processor will suspend the program being executed and start the exception service routine or ESR. This routine takes appropriate action to recover from errors. When exception processing is initiated as a result of such errors, the processor suspends the program being executed and starts an execution service routine, that is exception service routine. This routine takes appropriate action in order to recover from an error if possible, else informs the user about it. The second one is debugging. The system software usually includes a program called as debugger, which helps the programmer to identify an errors in the program. The debugger uses exceptions to provide two important capabilities. The first one is trace mode. When a processor is operating in trace mode, an exception occurs after execution of every instruction. So in the case of trace mode, an exception occurs after execution of every instruction. This uses the debugging program as the exception service routine, which enables the user to examine the content of processor registers, memory locations, and so on. After the processor returns from the debugging program, the next instruction in the main program is executed and the debugging program is activated again. During the execution of the debugging program, the trace exception is disabled. Trace made operation is also known as single stepping. So the second one is breakpoint. The breakpoint provides a facility to interrupt the program at specific points selected by the user. The user is specifying the respective point at which the program can be suspended. An instruction called trap or software interrupt is usually provided for this purpose. An instruction called as trap or software interrupt is provided for this purpose. The execution of this instruction causes the same action as hardware interrupt. While debugging a program, the user may wish to interrupt the program execution after instruction I in the program. The debugging routine saves the instruction I+1 and replaces it with the software interrupt instruction. When the program reaches to this point, the debugging routine is activated. So that is at ith location. So this gives the user the chance to check the register contents as well as memory contents. So the next one is privilege exception. So to protect the operating system from being modified by the user program, certain instructions can be executed only when the processor is in the supervisor mode. Such instructions are called as privilege instructions. When the processor is running in the user mode, it cannot execute an instruction that changes the priority level of the processor and enables a user program to access areas in the main memory that have been allocated to the other user. An attempt to execute such instruction will produce a privilege exception. So that means whenever the processor which enables some set of instructions to be executed in the case of user mode. So user mode which tries an attempt to execute privileged instructions. The privileged instructions need to be executed only when the processor is in the supervisor mode. So the privileged instructions are executed under user mode, so that is called as privilege exceptions. The exception occurred whenever the privileged instructions are executed under user mode.